Welcome to ACK to the Future, TCP in 2025. If we could please begin with the correct handshake. Sin? ACK. That's a TCP joke. Shall I tell you a UDP joke? Did you get it? My name's Philip Rowlands. I'm here with Jane Street. Please say hello at our booth downstairs. Now, I'm certain that everyone here uses TCP, and I'm confident that at least one of the ideas in this talk can help in your environment. So, something for everyone. The big idea on which TCP has more or less succeeded since 1974 is rate control without a central authority. In simpler terms, send as fast as you can until you can't. The big idea of this talk is that TCP tuning is worth paying attention to, making the most of the network capacity that you're paying for. We're going to discuss congestion, buffer sizing, and hardware acceleration. But let's start with a brief trip down memory lane. Just to reassure you, all the words in this talk are mine, but the stock photos are AI generated. I tried it the other way around, but couldn't take any good TCP-related pictures. TCP has survived for 50 years through being both extensible and backward compatible. Here are 3 examples. Window scaling. When a window size of 64 kilobytes proved to be too small, we didn't need to invent a whole new protocol, just a new TCP option in the 3-way handshake. Incidentally, this is why it's always useful to TCP dump, including the handshake, to allow accurate decoding of the other TCP headers. Selective acknowledgements. In the beginning was the ACK, meaning I have received this sequence number and everything before it. But when packets go missing, there was no way to express partial receipt of incoming data. The selective acknowledgement option allows us to confirm exactly what's missing, avoiding costly retransmits. And SYN cookies. Like so many protocols, TCP has its origins in a simpler time where malicious hackers didn't exist. To handle denial of service attacks, SYN cookies are an approach which avoids filling up the connection table with spurious entries. Those were just 3 examples out of literally hundreds of RFCs discussing TCP's design and implementation. Here's just a small sample, including RFC 1263, which argues in vain against protocol extensions, and 5841, an April Fool's joke RFC adding emotions to packets. Who said protocol designers can't have fun? But these are historical. This talk is TCP in 2025, and we'll be covering 3 main areas which discuss TCP performance and connection health, starting with congestion control. What is congestion control? It's the ability of TCP to vary the sending rate depending on the observed traffic conditions. If instead we negotiated some reserved bandwidth as part of the connection handshake, then adaptive congestion control wouldn't be needed. But network oversubscription is the norm. How busy is the network right now? When starting a connection, we don't know. There's nobody to ask, so we just need to start slow and get a feel for network congestion. If all of our packets are getting through, great, let's send faster. If some are not being ACKed, then slow down. This way, we can arrive at a happy level of throughput. Queuing theory, although fascinating, is not going to feature much in these slides. Many clever people over the years have proposed algorithms which not only need to be performant, but fair to others. Even within private networks, there'll be old devices running old and brittle software which we need to coexist with. Out on the internet, we can't dictate which tuning settings others should follow. Here are just some of the algorithms you may have encountered, and the 2 we're going to look at today are Cubic and BBR. Here's Cubic. It's the algorithm you're probably using out of the box on Linux and Windows and macOS. The name Cubic comes from a previous algorithm, BIC, and also refers to the 3rd exponent of the congestion window function. It's another TCP joke. Here you can see everything is working, there's no packet loss, and after a few seconds, we've reached a steady transfer rate of around 25 megabytes a second. Well, I've tricked you. This synthetic benchmark under perfect lab conditions is unrealistic, so let's sprinkle in some packet loss. This is the same test, but with artificial packet loss of 0.05% or 1 in 2,000 packets. To be clear, you could run per second pings for 20 minutes and wouldn't expect to detect this level of packet loss. What happens? Cubic is timid and backs off such that it reaches less than 1/5 of the baseline throughput. Here I've misled you again. Real-world packet loss tends to be bursty or correlated, not random. But the point of this slide is to illustrate a timid congestion algorithm. What do you suppose generative AI imagery looks like for timid congestion control algorithm? See, he's running scared of the packet loss. This chart is from a recent TU Dresden paper and shows just how poorly Cubic copes with small amounts of packet loss. So if Cubic is so timid, is there a more robust alternative? I just want to give credit here. This talk would not be possible without Wireshark. They're not paying me. It's not just a protocol decoder, but the TCP analysis and visualization features are invaluable for studying network performance. If you haven't seen them before, all the charts in this section are generated by Wireshark's TCP Stream Graphs feature. Here's BBR, which stands for bottleneck, bandwidth, and round trip. Two things to point out are the improved tolerance of packet loss and the indicated blips where BBR probes by allowing buffers to drain for a more accurate round trip time. I did read somewhere that BBR stands for buffer bloat reduction, but I don't think that's official. So if BBR performs better, why are we stuck on Cubic as a default? Let's talk about BBR's development. But before we can do that, let's talk about Quick. The development cycle for this stuff takes years, getting your changes into the kernel, waiting for users to rebase, etc. Google got bored waiting, so ditched TCP entirely and moved to UDP. Look at this bog standard search request using Chrome, where we see all the packets going to UDP port 443. The advantage here for Google is that you can iterate much more quickly on both the server and client side when you own the world's most popular website and browser. But Quick isn't a silver bullet. UDP isn't immune to congestion and dynamic network conditions, and the similarities between Quick and TCP include sliding windows, selective acknowledgement, and a connection handshake. Having worked on getting YouTube videos delivered faster over congested links, the benefits of BBR were eventually released to the Linux kernel in 2016. We now understand the motivation for Quick and BBR, but the kernel development cycle lag still exists, and BBR has been through various iterations, of which version 3 is the latest. I'm not here to tell Google any project priorities, but BBR version 3 has been living out of tree on GitHub for over 3 years. What you're seeing in mainline kernels is still version 1. Does this matter? Is there really any difference between the versions? Well, quoting the developer, Neil Cardwell, BBR versions 1 and 2 are obsolete, deprecated, and contain bugs. What's the problem with BBR version 1? One important aspect is fairness, whether it drowns out other congestion algorithms. Maybe we should consider the latest revision, version 3. The good news is that the fairness and retransmission behavior is improved. The bad news is that BBR3 lives out of tree on GitHub, is therefore harder to deploy, and doesn't benefit from many eyes of testing. We're not going to deep dive into the research behind BBR, but one distinguishing feature is the response to packet loss. But what if there was no packet loss? Impossible. Explicit congestion notification is a cooperative feature between endpoints and network devices to reduce packet loss. Avoiding packet loss avoids retransmission with its associated delay and detriment to throughput. It works like this. Some router along the path is busy, but not yet at 100% utilization, so it sets the congestion encountered bits in the IP header. Senders respond by slowing down. This way, packet loss can be avoided, or at least reduced. ECN support is pretty good in Linux and Windows and iOS. Apple is taking the lead in switching it on as an out-of-box default. But ECN won't get you anywhere without network cooperation. So check whether your favorite equipment vendor is able to add congestion encountered marking to a packet. In summary, not every packet will make it across the internet. But by choosing a suitable congestion control algorithm and looking at ECN features, which allow network annotated hints as to when to slow down, packet loss can be reduced and the response to packet loss improved. If you're in a congested network, how is Cubic managing with that? How easy is it to try BBR as an alternative? Would explicit congestion notification help? And do your network devices support it? In the next section, let's talk about windows and buffers. Not Microsoft Windows, not glass rectangles in the wall windows, but windows in the TCP sequence. Here is a admittedly weak analogy. Imagine a mail room where parcels wait to be shipped out or received. The size of the mail room is one of the factors which determines how fast we can send parcels. To make things interesting, you may have heard the terms receive window and congestion window. Well, we talked about congestion in the previous section, so from here on, it's just receive window. I'll say it again in a few slides, but getting this tuning right is vital for good TCP performance. Let's just ensure we really understand the performance implications here. TFTP is the world's stupidest file transfer protocol and works by sending and acknowledging data in lockstep. But by having only one packet on the wire at any one time, we're limited by the round-trip time. And here, the speed of light is unreasonably slow. For example, from Dublin to New York, we get only 12 round trips per second. That's far too low in throughput terms. So TCP is designed to have multiple packets in flight. So how many? This is the busiest diagram, so just take a moment. Here we see a flow of data from the sender on the left. When does data leave the send queue? When it's sent? No, when it's acknowledged. TCP is reliable. Any packet in flight might get lost. Therefore, note the unacked data still present in the send queue. TCP doesn't know when unread data will leave the receive queue, and also has to leave room for incoming packets in flight. If either of these queues fill up, then we have to stop sending. This is a stealthy performance killer. Stealthy because nothing is broken. There's zero packet loss, yet we're not using the full capacity of the network. Remember, this aspect of buffer sizing is controlled by the endpoints, not the routers and switches. In the orange box are the defaults from a recent Fedora installation. The third value is the important one, the maximum buffer size. Here, the sending value is lower than receiving, probably making the sender the effective bottleneck. Here's another way to visualize the buffer limits. The size of the receive window dictates the upper limit of the sequence number we can send. The size of the send queue dictates how much data can be in flight, not yet acknowledged. I've only shown these one way, but TCP is bidirectional, so duplicate all of this for the return data path. Remember, if we're looking in Wireshark, only the receive window is visible in the packet header. And these sizes are a hard limit on performance. It's vital to tune them correctly. So what's the magic number? To avoid this artificial bottleneck, we need to ensure that buffer sizes exceed the magic number known as bandwidth delay product. What is the BDP? In the general case, we don't know. When we talk to a random client on the internet, we don't know beforehand how far away it is or what bandwidth is available right now. So in the absence of a concrete BDP, what number shall we pick for buffer sizing? It's tempting to calculate and bake it into config files, or even worse, code. I would not recommend this approach, which is like setting traps for ourselves in the future. Rather, we can let the kernel auto-tune the buffer size on our behalf up to the maximum value we saw earlier. We do need to pick a maximum, though. In this example, suppose we buy a 1 gig circuit between Dublin and Seattle for the next SREcon. Then that would require 17.5 megabytes of packets in flight. Do you use 1 gig or 10 gig or faster WAN links? Do you talk to servers worldwide or transatlantic, or just in the same region. If we get this wrong, this staircase pattern will emerge when zooming in on your PCAP files. Each step is one round trip time wide and one window high. Look at all the flatline sections where we could be sending data if only the buffer size tuning was good. I would typically recommend making TCP RMEM and WMEM the same and larger than the largest expected BDP. Remember that we said only the receive window is visible to Wireshark. This filter, window full, will calculate when the unused window size drops to 0, but it can only do this when the PCAP file includes the TCP handshake, so always capture handshakes if possible. The other possibility, send queue full, won't show up in Wireshark directly, but we can infer it from the staircase pattern. Some congestion control algorithms avoid the staircase with a technique named pacing, which tries to send data at a steady rate instead of bursts, but in other respects, the same buffer constraints apply. In summary, your default TCP buffer sizing sucks, and you should change it. This section is probably the easiest return on investment because it's just kernel settings. You don't need permission from the network team. So work out your maximum bandwidth delay product, compare that to your maximum buffer size, and look for the hidden performance gap between them. Hardware offload. As interface speeds increase, problems emerge for TCP performance, such as shrinking amount of time available to process each packet, and the even distribution of work throughout the system. But over recent years, network hardware has gained the ability to handle increasingly complex tasks on our behalf. There are even approaches which dump raw packet data into memory and let user space processes handle it. In case you're wondering, we're not going to talk about NAPI or busy polling or interrupt coalescing because this is a TCP talk, and those are more like general driver optimizations, but you might still want to check them out. Let's look at some of the approaches to hardware offload. What do all these ETH tool settings mean? Why are there so many? Once we've optimized the performance from previous sections, we could be dealing with 10 gigabits per second, maybe more. That's getting close to 1 million packets per second, or 1 packet per microsecond. So anything the NIC can do to save CPU cycles will be beneficial. Let's start with the simple one, checksums. TCP inside IP, inside Ethernet, uses 3 checksums in different parts of the packet. Easy enough for the NIC to calculate. Checksum offload works for both transmit and receive. Checksums aren't complex, but an opportunity cost. Every cycle spent on CRC calculations can't be spent elsewhere. Let's talk about segmentation. Realistically, 1,500 bytes is the maximum packet size you'll achieve on the internet today. I know there are some fans of jumbo frames out there, but it's a world of config and compatibility problems. But TCP stacks can go much bigger if the NIC supports segmentation offload. The idea here is that we pretend to transmit, say, 12 kilobytes all in one go, set the sequence number accordingly, but the sending NIC takes its packet scissors and cuts up the megapackets into MTU-sized pieces. The receiving NIC takes its packet glue and attaches them back together. This isn't a feature that has to be negotiated by both ends, and we can split and recombine in different sizes. There may be a latency trade-off when you receive a packet if we wait just in case for the next one to arrive. And if you've ever noticed unfeasibly large packets in packet capture, this is the reason. Let's talk about flow affinity. In modern server-class NICs, there's support for multiple receive queues to spread the work around. But packets snake their way across the network, and there could be any number of TCP connections interleaved, for example, 3. What this diagram shows is the hardware splitting up each flow into a different queue. It's configurable, but a typical scheme is to use the source and destination address and port number, which are consistent for the lifetime of a TCP flow. 3 connections isn't very taxing, but this approach can scale up to thousands of flows across tens of queues. Let's talk about the heuristics of TCP health. NSTAT and ETHTool provide many counters, seen here, but are they positive or negative or neutral? I've added the color highlighting with my subjective opinion on a few of them, but your mileage may vary, and your network won't look exactly like this. So ask yourself, am I collecting metrics related to TCP health? And how would I know when the network is unhealthy? By the way, these are supported in Prometheus by node exporters ETHTool and NetStat collectors. Occasionally, though, hardware offload can be actively hostile to good performance. Here's a war story about one specific metric, TCP OFOQ, or out-of-order processing. In 2010, a paper from Fermilab was published titled, "Why Does Flow Director Cause Packet Reordering?" 15 years later, I read this paper, shook my fist at a nearby cloud, and disabled the particular offload feature which was causing the extremely high TCP OFOQ counter and the SAC responses evident in Wireshark. If you ever see these black highlighted lines in Wireshark, check the expert notes and do try to understand what's happening. I should emphasize that these unhealthy metrics don't have to be 0, but when you see 330 million out-of-order packets, something's gone wrong. The narrow lesson here is to double-check your Intel 700 series NICs, but I don't know what hardware you're running. The general takeaway is that hardware offload isn't magic, doesn't always do the right thing, and it's worth spending the time and effort to understand which offload techniques are useful in your environment, and eyeball the error counters once in a while. In summary, you're probably using hardware offload by default, and it does help to scale performance and reduce CPU overhead. Use the metrics provided by the kernel and network card to convince yourself that throughput is good and errors are low. May your windows be large and your packets delivered. Let's now end the conversation according to the sacred texts. Fin. ACK. Thank you.